Hello all, welcome to the next session on electronic devices. In the previous session we had come across the second topic in the fourth module, which is about the equivalent circuit that we had followed. That is a small signal equivalent circuit which includes the resistors, capacitors and a dependent source. Have to represent that and the variations of the same, and by including a single series source resistance, how does your transconductance gets reduced. We all saw that, and then we started off with what is called as a frequency limitation factor. There are two frequency limitation factors. The first frequency limitation factor was about the transit time, which I told you, which is related by an equation L by Vs, where L indicates the length of the channel and Vs indicates the saturation velocity with which the charge carriers are moving. Now, when does this transit time becomes of prominence is whenever we are dealing with the applications which is of high frequency. When we want to operate at high frequency, then the transit time becomes more of importance, because less the transit time, more will be the charge carriers that can move from between the source and the drain. That's how you can make the mode of the operation can be changed from one mode to another mode at a faster rate, and that is where that comes into picture. That is the transit time factor comes into picture. Now, what is the second limitation factor as? See, as we have looked into the small signal equivalent model, it also contains what are the passive elements it is being used in order to represent the small signal model. We had resistors and we had capacitors, right? Now, whenever I use capacitors, whenever we have a capacitor, then there is a charging and discharging process that takes place. Getting my point? Now, if in case I want to say it in the simpler terms, this is your structure. Now, what is this regions are? These are the depletion regions. Now, if I want to represent, there is a capacitance behavior that exists between the gate and the source. What does that basically indicates? We have a depletion region in between, and then we have accumulation of charge carriers in this region and in this region, which in turn make it to behave as what is called as a capacitor. Done. Now, will there be certain amount of time that is required for these charge carriers to get accumulated? Yes, and that is what we refer it as the charging time of the capacitor. Getting my point? Now, let me try to explain in that form and see how does the charging of the capacitor has something to do with the frequency. Done. Now, let me consider the equivalent circuit which has only the primary capacitors and the dependent source. This is your IDS value. This is your drain terminal of the JFET that I am considering. This is the source terminals and this is the gate terminal. Now, let me consider a current which is called as II, which indicates the input current. Now, what is this capacitance? This is the capacitance between the gate and the source. Therefore, let me represent this capacitance to be as CGS, and this capacitance which is between the gate and the drain to be represented as CGD. Done. Now, based on the time that it requires to charge the capacitors, what happens to the delay that is involved? We know tau is equal to RC, right? As the capacitance charging time increases, what happens to the delay that is involved? Even that will increase, which in turn will alter the operation of the particular JFET that I am considering. Therefore, it is very important for me to look into the charging time of the capacitors. Yeah, and that is the second limiting factor. What is the second limiting factor? Factor 2, which is the charging time of the capacitors. That's the second limiting factor. Done. Now, if in case, see what is this? There is a supply that I am giving. What is that? It is gate to source voltage. Now, whatever the gate to source voltage I am giving, if it is an AC signal, then obviously there will be certain frequency which is involved, right? Now, if I try to increase the frequency of this input signal that I am providing, what is that I am doing? I am trying to increase the frequency of which signal? The input signal that I am giving. Then what happens to the capacitance that is seen? We know the capacitive reactance is given by 1 by j omega c. Now, what does this omega factor indicates? It is the frequency component. What does this xc indicates? It is the capacitive reactance. Then, what about this c value? It is the capacitance value. Now, what am I trying to do? I am trying to increase the frequency of the input signal. So, if I tend to increase the frequency of the input signal, what happens to the total reactance that I am seeing? It tends to reduce, right? Now, as we increase the frequency of VGS, input signal VGS, what happens to the impedances of, which are the two capacitors, CGS and CGD? It tends to reduce, because we know the relationship. This is the impedance of the capacitor that I am meaning to say. So, we have two capacitors, therefore, both the impedances will tend to reduce. Now, what happens to the current which is flowing across CGD? It tends to increase. Therefore, the current across CGD will increase. Done. And this is how you can see that as I tend to increase or decrease the frequency of the input signal, it has certain impact on the impedances of the capacitance and the current which is flowing in the device. Now, if I consider the capacitor charging time as a limiting factor, then it is very much important for us to define a frequency which is called as the cutoff frequency. And how will I represent that cutoff frequency? It is represented by Ft. And what does this cutoff frequency indicates as? This is the frequency at which your input current magnitude will be equal to the output current magnitude. What is the output current magnitude? That means the magnitude of II is equal to the magnitude of IDS, and that is what it basically indicates. Got the point? What does Ft indicates? It is the cutoff frequency. Now, by keeping that in mind, let me try to represent the equation for IE. Let me try to represent the equation for II. How will I represent the equation? II, what is the basic equation? I is equal to V by Z, no? Here, what is that Z we have? Only the capacitor. How are these two capacitors connected? These two capacitors are connected in parallel. Whenever the capacitors are connected in parallel, what will be the total effective capacitance? It will be added up. Getting my point? Yeah. So, keeping that in mind, if I want to represent the equation for II, it is given as the voltage. What is the input voltage that I am providing? It is VGS into, see, what is Z here? Z is XC. What is XC? V into V divided by 1 by j omega C. So, if I alter, it will be V into j omega C. Now, what is that C here? The C here is two capacitors which are connected in parallel. That means we have to add it up. Now, what will be the term here? It will be J into omega into, what will be the C term? It is CGS plus CGD. I hope all of you got this. Yeah, where did we started off from? XC, we know that it is 1 by j omega C. We know how will I represent the current? It is V by Z. Now, what is Z here? It is just XC. How will I substitute XC as 1 divided by j omega C? When I cross multiply, I will be getting V into j omega C. Done. Now, which is the current that relates to in the circuit? It is the input current. Therefore, I have written it as II. And then, what is the voltage? Here I am providing it is VGS. Therefore, I have written VGS into j omega. And instead of capacitance, what I have to consider here? I have to consider the effective capacitance. How is the effective capacitance? Since both of these are parallel, I have to add them up in case of capacitors, and that is what I have written here. Done. Now, let me consider the CG value to be equal to CGS plus CGD. After that, what will my equation turns out to be? VGS into CG into j omega. Now if I want to represent the magnitude of the input, then it is basically represented as what is omega? 2 into pi into ft. What is the condition for cutoff frequency? We know the magnitude of the input current is equal to the magnitude of the output current. Therefore, I am trying to represent the magnitude of the input current, and if I want to represent omega, what is it? It is 2 pi f, and since here I am interested in the cutoff frequency, which will in turn relates to the charging time of the capacitor, which is a one of the limitation factors that I am considering. Therefore, I have represented it to be as ft into Cg into Vgs. Since I am considering the magnitude, the J term will not be taken into consideration. Done. Now, what is this equal to at the cutoff frequency? At the cutoff frequency, the magnitude of the input current is equal to the magnitude of the output current. Now, what is the output current equation? It is nothing but equal to Gm into Vgs under certain conditions. So, I will just write it as Gm into Vgs. This is nothing but the output current. Done. Now, out of these two, when I compare, therefore, what can I write my Gm to be equal to? It is can be written as 2 pi into ft into Cg. Therefore, how can I get the equation for ft? Ft can be written as Gm divided by 2 into pi into Cg. And this is the equation for the cutoff frequency, which is in turn related to the charging time of the capacitor, that is becoming a limitation factor in case of the JFETs. Done. And this is what the relationship is, where Cg is what? Cg is Cgs plus Cgd. Done. If I want to represent for maximum possible transconductance value, then the equation goes as follows. The Gm max is given by E into mu n into Nd into W into A divided by L, and this is the equation for the maximum transconductance that is possible. So, if the maximum transconductance is this condition and if the capacitance is minimum, the capacitance minimum gate capacitance is given by the equation epsilon S W L by A. So, what is the two conditions that I am considering? If the transconductance is maximum and if the gate capacitance is minimum. Now, for these two conditions, if I substitute these two over there and try to alter the cutoff frequency, then the cutoff frequency final equation will now be represented as follows: G into mu n into Nd A square divided by 2 pi epsilon S L square. And this is the cutoff frequency which I can observe when we have a maximum transconductance and the minimum gate capacitance. Got the point? Yeah. I'll just have a quick revision. What we try to understand, the factor 2, which is a frequency limiting factor in case of JFET, is the charging time of the capacitor. Now, how can I vary that? It is basically the function of the frequency of the input signal. So, as I tend to increase the frequency, we know it is inversely proportional to the impedances, therefore the impedance reduces. As the impedance reduces, we know the capacitance, what happens to the current which is flowing across the capacitor, it tends to increase. Done. Now, this indicates that there is a clear indication that the frequency of the input signal has something to do with the charging time of the capacitor. Done. After that, we considered a terminology which is called as a cutoff frequency. If I am using a charging time as a factor, then have to define what is called as a cutoff frequency. What is cutoff frequency? It is the condition where the magnitude of the input current is equal to the magnitude of the output current. And I have tried to represent the equation for the input current by using these basic formulas, and this goes as follows. After that, we assume the gate capacitance, total gate capacitance is CGS plus CGD. I substitute substituted, then obtained the magnitude and equated to the output current. After that we got the equation for the GM and then altered it to the cutoff frequency. Now once I am done with that, we have considered two conditions. What are the two conditions? That is when the transconductance is maximum and when the capacitance is minimum, gate capacitance is minimum. These are the two equations that you have to learn. We will not be looking into the derivation of this as such because it is out of scope. And then once we substitute that in the equation that I have obtained here, then the resultant equation is as follows. So these are the two equations that mentions about the cutoff frequency. Done. And this is about the second frequency limitation factor, and also we looked into the cutoff frequency as well. And this is about the second topic in the module 4. I hope all of you got this about JFETs. What did we consider? We understood the basic operation of P and JFETs. So there we considered an N channel, and then we tried to understand with different cases that we had considered, and also we had looked into the small signal equivalent model and which are the factors that affects the performance of the JFETs. Done. Now it's time to move on to the next topic that is present in the module 4, which is about Mosfets. So what does Mosfet stands for? It is metal oxide semiconductor field effect transistors. The third topic in module 4 is what is called as a two-terminal Mosfet. Done? Now, before going into this, let me try first to say what is a Mosfet. We will try to understand the working principle a little while later. Now, what is that we will be trying to understand in this particular topic is we will be going through the process of fabrication in order to obtain one of the kinds of the Mosfet. Done. So before that, we have to understand how many terminals we have for a Mosfet and what are all the different classifications that we can have under a Mosfet. Now, what does Mosfet stands for? It stands for metal oxide semiconductor field effect transistor. Done. M is derived from this O, S, F, E, T. Got the point? And that is why the short form MOSFET. Or in the textbook it is named as two-terminal Mos structure. Done. Now, we got to know the full form of MOSFET. What is this MOSFET? It's one of the categories of field effect transistors. We know why the name field effect transistors comes into picture. That is because the transistors has something to do with the electric field that is being generated, because of which the charge carriers are getting drifted from one terminal to that of another terminal, and therefore we refer that to be as a field effect transistor. We understood about the basic p-n junction field effect transistor, how it works. Now it is time to understand about the metal oxide semiconductor field effect transistors, which is one among the classifications of FETs. And this is also an unipolar device. That means the majority charge carriers are the ones which is responsible for the current flow in the device. It is either the holes or it is the electrons that is present that is involved in the current flow. Done. Now when I consider a MOSFET, there are basically two classifications that I have. I have already mentioned in the very first class of the module 4, but still I feel it is important to repeat it again. That's why I am doing it. So MOSFET, what are the two classifications? One is called as depletion mode MOSFETs and other is referred as enhancement type of MOSFETs. Done? Now when I again want to classify among these two, again it is classified into NMOS depletion type MOSFET and PMOS or P channel to be specific. Okay. This is N channel depletion type MOSFET and again we have a P channel depletion type MOSFET. Again in case of enhancement we have an N channel and a P channel. Done? So this is regarding the classification tree for a MOSFET. Now we'll first try to understand what is this two-terminal Mos structure or two-terminal MOSFET. Done? After that we'll look into the fabrication process. Now first let me tell you why it is called as metal oxide semiconductor field effect transistor. Let me consider the Mos structure. Yeah, and this underlying material is what we call as substrate. Then this is called as an oxide layer which is an insulator. What is this insulator? Which kind of material it is? It is an oxide layer and this oxide has a permittivity of epsilon OX and it has a thickness of TOX. And then we have this layer which I have shaded in blue which indicates it is a metal layer and then we have an ohmic contact here and these are the two terminals that I can extract. Yeah, and since here we are representing only two terminals and therefore the name two-terminal Mos structure. What does Mos here indicates? Metal, we have a metal layer, then comes an oxide layer which is acting as an insulating layer followed by a substrate which is made up of a semi-conducting material which is silicon and therefore the name two-terminal Mos structure. Got the point? Clear till here? Any doubt? Yeah, please get this point. So that is what the two-terminal Mos structure basically indicates. Done? Now let me try to explain you an N-channel MOSFET. First let me tell you what is the basic structure of the N-channel MOSFET and once you are done with that, now let's see how to fabricate that N-channel MOSFET. Yeah? Which is the kind of MOSFET I am considering? It is an N-channel MOSFET that I am considering. Now to be specific, we will be looking into N-channel enhancement type MOSFET. Done? I'll tell you what is the basic difference between enhancement and depletion type. When I consider a depletion type MOSFET, there is already a built-in channel that is present between the source and the drain. Whereas enhancement type, you are supposed to create the channel. There is no channel as such between the source and the drain. You are supposed to create the channel by applying certain biasing. Done. Now what is that I am considering here? It is the fabrication of the MOSFET that I am looking into and which kind I have considered. It is an N-channel enhancement type MOSFET. Now if in case I want to represent that symbol, it goes as follows. See, whenever I consider a MOSFET, there are basically three terminals: gate, drain and then the source. And at the underlying layer. What was the underlying layer that we considered? It was the substrate, right? Hence, this one we have, which is called as a substrate or a body, is always shorted to the source. Therefore, we are connecting it together. Done. And if in case I am considering the N channel, the channel is of N type, and therefore the inwards direction I have to follow. Yeah, and since it is enhancement type, there is no channel between the drain and the source. Hence, there is a separate lines that have to consider for all three of them. That is the drain, this is the body or the substrate which is shorted with the source. Both of them are at same potential. Therefore, we have shorted it and completely represented as source. And then we have a gate terminal. We have a separate line which indicates there is a gap between, which indicates there is no channel which is built in between the drain and the source. And this is the symbol of an N channel enhancement type MOSFET. Now, if in case I want to look into the cross section view of this kind of a MOSFET, it goes as follows. We have two N plus regions which is formed upon a P type substrate. Done. And then this forms the source, this forms the drain terminal. And then what is the other terminal that we have? It is the gate terminal. So how is the gate terminal is being formed? We know what is the name. It is the metal oxide semiconductor. Therefore, we have to have a metal layer which I am shading right now. Done. And then we have an oxide layer, and beneath that we have a semiconducting layer, and this is where the gate terminal is being formed. Now, when I consider this kind of a structure, this is an N plus NP, this is N plus NP, and therefore what should be there in between? There has to be a depletion region, and that's what I have shaded and represented. The cross section view of NMOS. Now, before going into the fabrication of MOSFET, Now let's try to look into the fabrication of MOSFET. Before going into this, it is very much important for you to understand a terminology which is called as a photoresist. What is it? It is a photoresist. Now what is the meaning of photoresist as the name itself indicates, it is something which is related to the light. Yeah, and this is a kind of material that is deposited on any kind of semiconducting layer. And what is the purpose of depositing this is, this kind of layer is a light sensitive material, and whenever I make a light to fall on this kind of a material, it reacts to that, and then either it will become strong, it becomes insoluble, or it becomes solvable. Now why am I using this photoresistors? In order to get a pattern upon the underlying layer, I will be using this photoresist. As of now, you just remember what is photoresist. It is a light sensitive material, and whenever it is exposed to UV light, what will happen? It will either become insoluble or it will become solvable to whatever the PR developer, that is the photoresist developer that I am inserting into. There are two different kinds of photoresists. One is called as positive photoresist and other is referred as negative photoresist. Yeah, first I'll tell you what is this positive and photoresist and negative photoresist, and then we can go into the fabrication steps. Now if in case I'll consider that there is a silicon substrate. Done. Upon that I'll try to spin coat. What is that? The word I used, it is spin coating. That is, this silicon substrate is in the form of wafer. So upon that wafer, I'll keep it on a disc like a structure where it spins. Upon that spinning disc, that is the silicon wafer that I have, upon that what will I coat with? It is, I'll be coating with what is called as a photoresist. Yeah, so what is that I am coating with? A photoresist. In the short form, I'll refer it as PR. Done. After that, I'll be putting up a mask and that mask is of a structure like this, wherein it has certain transparent regions and the opaque region. Upon that, I will be making my UV rays to fall on. This is the UV rays that I am making to fall on. Now, since these are the transparent regions, what will happen to the light? The light will fall on this photoresist. Here also the light can easily fall on the photoresist. Done. Whereas here at this region, it is in which form? It is in the opaque form. Therefore, whatever the light, it gets blocked and no light falls on this particular region. Got the point? Now, based on whether I am using a positive photoresist or a negative photoresist, I can know whether the exposed regions becomes solvable or insoluble. Yeah. Now, let me consider both the cases. One is the positive photoresist and other is the negative photoresist. In the positive photoresist, the ones which is exposed to the UV rays becomes solvable. So, what is the meaning of solvable? Means when I dip this into whatever the wafer that I have, this is the wafer structure, this is how the silicon wafers will be. Now, when I dip that wafer structure which is spin coated with the photoresist onto a PR developer, what is that I am mentioning? PR developer, which is a photoresist developer. What will happen is, whatever the regions that I have, when I expose it to light, if in case it is a positive photoresist, the ones which is exposed to light become solvable. As a result, I can have a photoresist only in the region where it is not exposed to light. That is what I have represented. Done. Now, if in case I consider a negative photoresist, how is the behavior? The ones which is exposed becomes insoluble whenever I dip it in the photoresist developer, and the ones which is not exposed becomes solvable. Therefore, where all I can have the photoresist, in these regions I will be having the photoresist, whereas in this region I will not be having the photoresist. And this is the difference between the positive photoresist and the negative photoresist. Done. Always remember, in the positive photoresist, the areas which is exposed to light becomes solvable, and in case of negative photoresist, the areas which is not exposed to light becomes solvable. Done. And this is regarding the basics that you have to understand. Now, let us go into the fabrication details of the MOSFET. Now, we shall start off with step number 1. So, what is that we have? Always remember, first whenever we are doing fabrication, we will be starting off with what is called as a wafer. Done. And this is how the wafer looks like, and that will be in the disc form, and that is basically made up of silicon and which is being represented as a substrate. And that is what I am represented as, a silicon substrate. Now, what is that the underlying substrate should be of? When I want to have an N-channel MOSFET, it should be of a P-type. Therefore, what kind of doping I have to do for this? It is a P-type doping, that is a trivalent doping I have to do, and then the resultant I will be getting as a P-type substrate, which is a P-type silicon substrate. What is step number 1? We are starting with P-type silicon. Yeah. After that, we will consider step 2. Now, what is this step 2 is, whatever the P-type substrate that I have considered, upon this P-type substrate, I will be performing oxidation. That is, we already have a silicon wafer, and for that silicon, if I perform oxidation, what is the resultant that I will be having? It is the silicon dioxide layer that I have formed. Now you might question me, what is the purpose of having this silicon dioxide? What is the silicon dioxide? It is an insulating layer. Why am I creating this insulating layer is, if I grow the silicon insulating layer completely upon the p-type substrate, then I can ensure that this semiconductor will not react to the upcoming layers at unnecessary regions. I can only make this p-type substrate to have contact with the rest upcoming layers only at the regions where I wish to. Yeah, or else I have to isolate them, right? For that purpose, I will be using what is called as an insulating material. How am I forming this insulating material is by developing or by making the silicon substrate to react to the oxygen and then form a certain depth of the silicon dioxide, which acts as an insulating material, and that is nothing but step number 2. And how will I represent that step number 2? It is oxidizing the silicon. Done. After that, let me consider step number 3. What will I do with the step number 3 is, I have a p-type silicon underlying substrate, and then we have an oxide layer, which is what it is, a silicon dioxide insulating material, and upon that I will be trying to deposit or spin coat what is called as a photoresist. And here the kind of photoresist, let me consider it to be as a negative photoresist. So what am I spin coating that with? I have formed a silicon dioxide, and then I'll keep it on an instrument in such a way that it will spin, upon which I am depositing the photoresist. And what kind of photoresisting material that I have used? It is a negative photoresist. Therefore step number 3 is what? Depositing, or step number 3 is spin coat negative photoresist. Done. Therefore, what did I do? I have spin coated with a negative photoresist. After that, what will I try to do is, upon this, I'll use a mask, and then I'll let the UV rays to fall on. So, exposing to UV rays. Done. How will I show that? I'll use this structure. Now upon this, what all we have? We have a p-type silicon, and then what does that we have? Let me follow this way of hashing for a silicon dioxide, and this way of hashing for the negative photoresist. Done. Upon that, let me use what is called as a mask, and then this mask is having the opaque regions over here, and these regions are transparent. Done. After that, I'll make the UV rays to fall on this. And what is this? This is UV rays, and this is mask 1. Let me name this as mask 1. After that, what will happen is, see, since I am using a negative photoresist, remember, when I use a negative photoresist, whatever the ones which is exposed to light becomes insoluble. Therefore, this region, I'll just highlight this like this. So, these are the regions which is not exposed to light, whereas this region and this region and this region are the ones which is exposed to light. So, once the one which is exposed to light becomes what? They becomes hard, whereas the ones which is not exposed to light becomes soft. And since they have become soft, what will happen when I dip it in the PR developer? They tend to get solvable, and these portions will be removed. So once they are removed, what will I try to do is, the next I will be getting like this. So this is your p-type silicon that I have, upon which we have silicon dioxide, Done? And then only these are the regions where, okay, yeah, these are the regions where I will be having the negative photoresist. Clear till here? Any doubts? No? Where did we started off with? We started off with a silicon substrate and we doped it with a trivalent, thereby we obtained a p-type wafer. After that, what did we do? We performed oxidization by in order to ensure that there is an insulating layer that we obtain, and what is that referred as silicon dioxide. After that, we spin coated what is called as a photoresist, and which kind of photoresist have used here? It is the negative photoresist. Once we are done with that, we are depositing a mask on that and we are making the UV rays to fall on. In this mask there are certain regions which is opaque and there are certain regions which is transparent, and these are the regions which lets the light to fall on, whereas these regions blocks the light. We know whenever I am using a negative photoresist, the one which is exposed to light becomes insoluble and the one which is not exposed to light becomes soluble, and therefore dip in PR developer. So once I dip it in the PR developer, this is how I will be getting the ones which is not exposed becomes solvable, and the rest places where I will be having the negative photoresist. Now why am I doing this is, as you can see, there are two N plus regions that I have to form in order to obtain the source and the drain regions. That is why only in this regions I have to etch the silicon dioxide so that I can what is called as perform doping only in this regions with the pentavalent impurities and obtain the N plus wells. Yeah, what are these called as wells? Which are the two N plus wells that we have in order to ensure to happen that we are performing all these things, that is depositing a PR, then exposing it to a mask through an UV light, exposing it to a UV light through a mask, and then obtaining the structure. Now what I will do, I will perform etching of the silicon dioxide. Number 6, there are three things that is involved. First, I will perform etching of silicon dioxide. Here I will be etching the silicon dioxide. After that, what I will do, diffuse the pentavalent impurities. Done. After that, remove negative photoresist using what? The PR developer. After doing all these, the resultant that I will be getting is, I will have an p-type silicon substrate, and then these are the regions only where I will be having the silicon dioxide. And what is that I am doing? I am trying to dope it with pentavalent, which forms what is called as N plus regions. Done. Always ensure to have a little extension here. It will not exactly stop at right at this. Yeah, there will be a little extension that takes place, and therefore ensure to show from here to here. There is little extension that you have to show at both the cases. And this is the structure that I have got. Now, after this, what do I have to have? I need to have a metal contact to get the source terminal, drain terminal and the gate terminal. And the gate terminal here in this region I am still not completed, because we know what all it should have. It should have a silicon dioxide and a metal layer. Therefore, upon the silicon dioxide I need to diffuse a metal layer. I need to have a metal layer which will form the gate region. Now, in order to do that, we have further more steps that have to be followed. So, what I will do in step number 7 is, I will be again developing a photoresist upon this silicon dioxide. Completely I will spin coat with the photoresist. Done. What was the hashing I used? This is the way I have represented. Done. What is this? Negative photoresist. Now upon this what I'll do, here is the region where I have to etch the silicon dioxide little bit and I have to infuse or I have to put up the metal layer. Therefore I'll be ensuring that only in this region I'll make whatever the solvable things that I have to do, whereas the rest all PR is kept as it is. And in order to do that, we need to have a mask, right? And let me consider that. So we have two N plus regions. We have P-type silicon. Done. And this is what? Silicon dioxide. Now we have a photoresist developer all over it, and this is the hashing that I am following to represent the photoresist. Upon that, what am I trying to do? I am trying to have a mask. Let me represent this to be as mask 2. Done. And this is where I have to have a solvable thing, therefore I'll darken this, and the rest all I'll make it as transparent. Upon this, what am I trying to fall on? I'll try to let the UV rays to fall on. Now once I'm done with that, what happens to this region? This is the ones which is exposed to PR, therefore they becomes insoluble, and this is the region where the PR becomes solvable. Now once it becomes solvable, I'll remove this PR and then etch the silicon dioxide a little bit, and then the resultant is what I'll be getting now, which is step number 9. What will I do? Remove negative PR at gate, then etch the silicon dioxide at to form gate region. Now once I do that, after that let me specify the other places as well. After that, then what again have to remove the all over the rest all PRs as well, right? So once I am done etching the silicon dioxide, once I am done etching the silicon dioxide, this is the structure that I'll be getting. P-type silicon. These are the N plus regions. And then dip in PR developer. So what did I do? I removed the negative PR here first at the gate and then etched the silicon dioxide, and then I dipped it in the PR developer to remove the overall photoresist, and this is the structure that I'll be getting. Now upon this, what I'll try to do is, in step number 10, I'll be depositing the metal all over. If I want to consider that and represent the structure for step number 10, the structure goes as follows. So this is the P-type silicon material. We have N plus wells. Done. Upon this, what am I depositing? I've told I am depositing aluminum, which is a metal layer. And this is the aluminum that is being deposited. Now once I am done with the aluminum deposition, I will etch the aluminum wherever I am not required, and the rest all wherever I want to form source, drain and gate. That is the regions where I will be keeping the metal contacts, and the resultant will be as follows. So this is where I will be getting the source, gate and the drain, and this is step number 11. What is that I am doing? I am etching the aluminum wherever it is not required, and wherever I want to make a contact, only there I will be keeping the aluminum, and this forms the typical structure of the N MOSFET that I considered, and these are the steps that I have to follow in order to fabricate a MOSFET. So the example that we considered is for an N type. So if you know this, then you can do it for P type by yourself. I hope all of you have understood the fabrication process. In the next class, we will be looking into the energy band diagrams related to MOSFETs and its working principle. Thank you one and all.